Hello everyone, and thank you for tuning into my talk about the Fern. The Fern is the Southern Hemisphere's first passive house multi-residential building, and I'm going to take you through behind the scenes of how it came together. Now, the first question that one must ask about a project like this is why? Why did we do it? Well, we wanted to demonstrate that architecture can not only be functional and hopefully beautiful, but also take account of its environmental context and the wider environmental context of the world and be as responsible as possible. Now, speaking of architecture, this is Mies van der Rohe's Farnsworth House, as many of you will know. This is held up as one of the great icons of modern architecture. But what did the client think? You burn up in the summer and freeze in the winter because nothing must interfere with the pure form of their rectangles. So she wasn't too happy. And similarly, this is Le Corbusier's Villa Savoie. And the client said about this one, after innumerable demands, you have finally accepted that this house, which you built in 1929, is uninhabitable. Please render it inhabitable immediately. I sincerely hope that I will not have to take recourse to legal action. So architecture has had a bit of a misfocus around environmental issues. So would you be getting this man to design your house? No. What about this man? No. This man? Maybe. Now, to the Fern, here it is in context, quite close to the Sydney CBD, lovely park across the road, train station very close by, fantastic location, except that you get 40,000 cars going past every day. And it's very busy, noisy, dusty, all the things that you want to avoid when you're in one of those great city locations. So we have long north boundary, the sun, good solar access, except that we had to put firewalls either side, which means that we're left with only east and west unfavorable solar access. So your passive solar is pretty much gone, unfortunately. Couple that with the 40,000 cars going past every day, and what we really needed here was to create a bubble, an oasis, which could be a serene place in the middle of the hustle and bustle of the city. And we chose passive house for its energy efficiency, thermal comfort, occupant well-being, and we hoped return on investment. First thing we had to do was get the Passive House Institute to generate Sydney climate data because nothing had been done in Sydney at that point. Here it is, and that's now available for everyone to use, and I hope you do get the chance to use it. Then the building was modeled in the SketchUp plugin. This is mirrored for Northern Hemisphere. Apparently now that's been corrected, so you don't need to do that these days. And we generated Claire Parry generated the parameters that we would need to meet. Now, interestingly, for insulation, the wall is required to be R3.5, which is R3 insulation on a concrete wall. That's actually not that far above compliance. Similarly, floors suspended and on ground R1 insulation. That's as low as it gets. Roof R4 insulation. We actually built it to about R7 just to be safe. But again, it's really not that far above compliance to achieve passive house in terms of insulation in Sydney, which is good to know. What we did find was way above compliance was the glazing requiring 1.6 U value of 1.68, which is about 4 or 5 times better than compliance. And that's because largely because we had large areas of east-west facing glazing for the reasons I've just explained. And interestingly, the entrance doors to the apartments, a U value of of 2 or less was required. There's virtually no information available on U values of fire doors, which these apartment doors had to be. But we managed to get the ingredients from Corinthian and I believe it was vermiculite core, and that was modelled in therm and found to be a U value of less than 2, so that was compliant off the shelf, which is good to know. So obviously the fire insulation reduces heat transfer, which is what you would expect. These are the remaining parameters, which I won't go into because I'm sure you're pretty familiar with. And these were the peak cooling loads: 2 kilowatts in apartment 10, and heating loads, highest heating load of 1.4 in apartment 3. And the modelling showed that it would never get over 28 degrees no matter what. Heating balance summary. Interestingly, our roof ceiling component here is very small, which is one of the advantages of multi-residential construction, that your one apartment's roof is the next apartment's floor, so you get that economy of surface area to volume ratio working in your favour. So that would be much larger in a single house. Another reason to try passive house in multi-res. And similarly for the cooling, I won't go into that in too much detail, but that was the balance that we started with. And where did we actually start? Here, where it was a squat, had a colourful history and was falling down, so we gave it a little bit of help and were soon on our way to building. Now, we did build the Fern out of concrete. We used the 3-point Green Star mixed concrete, which has a lot of the cement and aggregate replaced with industrial byproducts to reduce the embodied energy. I would love to have done it out of CLT, but given we were the basement underground and then the ground floor partially underground, it would have meant swapping from concrete to CLT halfway through, and it was just too much at that point in time. So we built the whole thing out of concrete. We used this reusable modular steel formwork to minimize waste, and it gives you a lovely smooth off form. And one of the other advantages of this system was that we could clip together up to 10 panels and lift them and move them from one wall to another, which gave us economies during construction. Now, on to the top 5 of the passive house system: structural thermal breaks. We divided the building into the east and the west wing with a circulation core in the middle. So we needed breaks where the insulated area had structural connections to the uninsulated. Similarly in section, you can see our entry from the street here, the service core and circulation core, the east wing and the west wing were insulated. We also used dance floor / recording studio sort of technology to create an insulated internal skin where we were below ground, and structural thermal breaks were required wherever we had balconies, etc. Now, the off-the-shelf units are great because they mean that you can cantilever concrete balconies, but they're designed for Northern Hemisphere winters and were overkill for what we needed in Sydney. And seeing as we didn't have any cantilever balconies, we adapted these acoustic dowels. So these are designed for acoustic separation, having one side coated in rubber, but it worked well for our purposes. We just installed them over a 30mm sheet of rigid XPS, biomassic top and bottom, fibre cement either side to hold it in place, and it passed the therm test. We had one of these dowels at 900 centres, which is a lot less steel passing through the thermal joint than conventional reinforcing, which and it also gave us our balcony set downs. So it provided the formwork for the balcony set down. So you can see them here being installed. We welded just to be safe in certain areas, and they work pretty well, I have to say. I would definitely do that again. Similarly, on walls, we used the this was more of an issue on the walls using the modular formwork. It would throw it out. We had to come up with a system of fixing it in place in the wall formwork. That was quite a lot of work. So one thing you should definitely consider is wrapping balconies and protrusions in insulation instead of using thermal breaks, because you may well find that that's a more economical solution depending on the specifics of the project, of course. Now, the super insulation, as we've said, isn't actually that onerous for Sydney because we have a fairly mild ambient climate. We used 100 mil structural insulated roof panel, which got us all the way for passive house compliance. We put bats in the ceiling below just for good measure. And on the walls, we had these structural insulated panels made as cladding, 50 mil PIR with magnesium oxide board either side, which was then just painted, fixed with a concealed fixing on a tongue and groove, and then paint finish. You can see there the tongue and vertical tongue and groove as well for water exclusion, and that worked reasonably well as well. We'll do that again. Now, high performance doors and windows, we used timber framed aluminium clad, aluminium with a thermally broken frame was not adequate for our project, probably because we had the east-west glazing only, and timber was more expensive and also more maintenance from the outside. So we used this blended system, which gives you the durability of aluminium on the outside and the thermal insulation of the timber as the structural frame. Now, we used an older style European system, and we needed triple glazing to hit our U values. You can achieve 1.4 with double glazing, but the triple wasn't a problem because it helped with our acoustic insulation anyway. And it was about 6 times more energy efficient because we were at about 1.2 to 1.4 U values, about 6 times more energy efficient than basics compliant would have been. And there's no reason in a passive house building you can't have lovely big openings. These lift and slide doors, which slide out of the way to give you that inside-outside living that people love. There's no reason you can't have that in passive house. It's a bit of a misnomer that people think it has to be sealed up all the time. And next we move on to air tightness. Now, this really is the elephant in the room in Australian sustainable architecture. This is a sustainable house, supposedly sustainable house, and you can see all these leaves on the timber floor. All those leaves actually blew in while the door was closed. So you can imagine, it's very pretty architectural detailing with this very minimal sill transition, but you can imagine how much, what sort of drafts they're getting. It's virtually impossible to heat and cool the space like that. So we used blower door testing to achieve our 0.6, and I have to say that this was the hardest thing to achieve in terms of the passive house compliance, especially for multi-residential. You've got so many different trades. to manage scheduling and a lot of different places to keep an eye on at once, making sure trades aren't penetrating your air barrier, etc. So that's something that you really need to be taking a lot of care with in your pre-planning stage if you are looking at doing airtight multi-residential buildings. And as you probably know, Passive House is around 40 times more airtight than the New South Wales average home, which is 20 air changes per hour, according to the CSIRO. And yes, we do live in CIVs in Australia. Now, heat recovery ventilation, I'm sure you're all familiar with how this works, so I won't go through the basic principles. In terms of multi-residential installation, I would strongly suggest you don't do what we did, which is install it in bathroom ceilings. This was a design we had done by someone early on, which turns out to be a really bad idea, because the other thing that's happening in bathroom ceilings is a lot of plumbing, and there were a lot of clashes and a lot of work going into setting it out around plumbing and coordinating that, which really didn't need to happen if we had put the HRV units in high-level cupboards, of which we had plenty. That would have been easier to service in future for changing filters, less clashes with other services, and also easier to access instead of having large ceiling panels which need to be dropped down to access the unit and just open a cupboard door. So we needed to take fresh air in from the open air lobby here, and we exhaust it out into the lift shaft or into the stairway, and supplied and exhausted as indicated here. There was a fair bit of ducting, especially through the 2-level apartments. And again, this is something you really want to do a lot of pre-planning, and it's definitely worth doing your services coordination with all your plumbing, electrical, HRV before you get on site, because that will save you a lot of money and headache on site. We use these great Zender combined manifolds and acoustic attenuators. So in the one unit, they take you from your large indoor-outdoor air supply into 6 internal pipes, as well as giving you acoustic attenuation, and they were quite easy to use. So that's something I'd recommend. We had some real snakes and ladders going on, having to use flat ducts crossing over to keep to our ceiling height in certain areas. So again, we were sort of fast tracking because we were doing the Passive House design as we were building, because it was pretty new to us. But there's a lot of knowledge out there that you can draw on to avoid this sort of thing. Now, something that's significant about this project is it's the first in Australia to use heat recovery ventilation as an NCC compliant wet area evacuation, or wet area ventilation system, and that was by virtue of a CFD, computational fluid dynamics report, which compared the standard to the Passive House and actually found that Passive House is superior to the standard system, which uses a high-speed fan for a short period of time. Found that you're actually better off using lower speed fans 24/7, and you get cleaner air. So that this was accepted by the principal certifying authority on the project, and that is now available for anyone to use across Australia. So I do encourage you to get in touch with AFA and see if you can get your hands on that. And another thing which is notable with the Fern is that we did an as-built model and through NatHERS and came out with between 9.3 and 10 stars for the 4 units that we modeled, which shows that there is crossover between more conventional and passive house systems. Now, beyond the top 5 of passive house, we put a truckload of solar on the roof. We actually had to get brackets custom made to fit it all because we were so greedy with our layout. But it does give us 21 kilowatts, and yes, it was like playing Tetris trying to get them on there. Now, the outcome of this is that in the August to November 2019 period, we used 4,751 kilowatts, and this is when the building was fully operational as serviced apartments, and we generated 5,651. So it generated 119% of its energy requirement, making it net positive in that period. In November to February 2020, so through the black summer heat waves, again generated more than it used, 106% of its usage. And then moving into autumn, 16th of Feb, 28th of April 2020, 105%. So over nearly a year, it's consistently been net positive in energy, which is something that we're very pleased about. Now, we did use ironically, we went to a lot of effort to create a private network, an embedded network for electricity, which enables the solar and the electric hot water, which is heat pump driven, to all the electricity to be individually metered down to very fine grain to incentivize people, occupants, to use less and to reward them for doing so. I say ironically because we then repurposed the building as serviced apartments instead of strataing and selling to individual home owners, as had been the original intention. So all this is dormant, but we still learned a lot, and be more than happy to share that learning with anyone if they're looking at doing something similar. Now, what we did do is we compared a commercial offer of an embedded network manager, which was, these were going to be the costs, and that was going to cost us only $2,000 up front, but over 50 years it was going to cost the owners $152,000. Instead of that, we worked with SATEC to basically do the design and implement the network ourselves, which cost us $9,000 up front, but was only going to cost $90,000 over 50 years, so saving about $60,000 for the owners over the life of the building if it had been sold off to individual owners. So we are using the Expert Power Pro software, the all inputs, all electricity usage, common area, individual apartments, heat pumped hot water, solar, grid, everything is individually measured, and the system we're going to use is that on each, instead of having a monthly bill, each time you have your quarterly strata fees, there would be an offset for your electricity usage, and if you'd used less than your allocation, then you get a credit. If you'd used more, then there'd be an addition to your strata fees. So it would be quite easy to operate as well as manage. Easy for the homeowners to operate as well as for the building manager to manage. And we did actually do a lot of work in predicting the usage we did a spreadsheet which included everything, including toaster, kettle, Wi-Fi router, modem, etc. And we then took the wattage for each one of those and did 3 models, one for summer, one for winter, and one for spring/autumn, and predicted on a sort of aggregated basis on an hourly breakdown whether this item would be used. So you can see for the HRV, that's going constantly 44 watts per hour. The kettle is being used just for 1 hour at 6 a.m. and that gave us the estimated usage, which then informed the number of solar panels we put on the roof, which I'm not sure if this actually served any purpose because we probably just would have filled the roof with as many solar panels as we could regardless, but there you go. Now on the hot water, we used heat pumps, and the heat pumps are powered by the solar electricity, and each one of these heat pumps, there's 300 litre tanks, and each one of those produces around uses about 550 watts, and ironically the booster, which serves just the ring main, uses about the same amount of electricity. So it just shows how efficient these heat pumps are compared to a conventional electric system. These are the pulse meters, which we used for each hot water line going into every apartment, and this sends a pulse for every litre back to the smart embedded network, to the smart meters, and that's how the system records the amount of hot water that each apartment is using, and aggregates that back to a cost per litre, which could be fed into the bills. So that's how the whole system works together, and the green walls up the center of the building cool the air where you're drawing in for your HRV, and provide a bit of a psychological lift as you come in out of the gritty city into this urban oasis. There's an underground rainwater tank, which collects all the rainwater, then irrigates up through the green walls and drains back to the tank, so you get a semi-closed loop for any runoff. And the air conditioning that we used the first 7-star 2 kilowatt air conditioners on the market. Each one of those uses 450 watts maximum, which is less than a quarter of a conventional 2000 watt plug-in heater that people buy at your department stores. So an equivalent basics compliant apartment would have needed an 8 kilowatt air conditioner, which just goes to show how efficient the passive house method makes the apartments. Now, all this is really aimed at developers assisted by able professionals such as yourselves, because developers will spend money on things that they think are going to give them a return. For example, they'll say we need European appliances, stone bench tops and recessed downlights in their apartments, even though they cost more than alternatives, because that's what sells these days. So by doing the Fern, we hope to demonstrate to conventional developers and to homeowners what's possible and what a superior solution is for comfort, cost savings, and the environment at large. So hopefully sooner rather than later, we'll see developers saying we need double glazing, solar panels, and HRV, because that's what sells these days. So all the best with your upcoming projects. Thank you very much.